Hello everyone. In this lecture I am going to discuss about energy storage capacity and fatigue loading of mechanical springs. This is from the course DMM1. So in this yesterday's lecture, here there is some problem. We got this W 500 newtons. In the problem it is given that for the load range, the axial deflection of the spring for the load range is 6 mm. Here the load range is 2250 to 2750. If you do the calculation, 2750 minus 2250, you will get 500 newtons. That will be the load range here. So here the load range is 2750 minus 2250 for 500, that is 500 newtons. And this is for 6 mm deflection. And here we are finding out the number of coils based on that load, because the 6 mm deflection is given for the load range of 500. By using that we are finding out the number of coils. Okay, and the maximum operating load of this spring is 2750 newtons. For that 2750 newtons we have to find out the deflection maximum. Delta max by 2750 is equal to 6 by 500, where these two are given. 6 mm deflection for 500 newtons load. Okay, by this cross multiplication we get that delta max is 33 mm. From that we can find out the free length of the spring and also pitch of the coil. Okay, by using that free length. Let's see energy stored in helical springs of circular wire. This is energy stored. Generally we know that energy storage is denoted by the triangle, okay, which the area of the triangle, which will be half W into delta. If you draw a graph between W and delta, we get that half W into delta is the area of the triangle, which will represent the work done or energy stored. Okay, that is the energy stored. This is U is the energy stored, which will be equal to half W into delta, which we have learnt in earlier classes also. We have already discussed that the maximum shear stress, this is the maximum shear stress value, which we have learnt, K into 8WD by pi d cube. From this we are calculating the W value, because we want W and delta in order to calculate the energy stored. W is equal to pi d cube into tau by 8 kd from this relation, maximum shear stress. And we also know the deflection equation, delta is equal to 8WD cube n by GD power 4. We need to simplify this relation by substituting the values. Here the W is equal to pi d cube into tau by 8 kd. Pi d cube into tau by 8 kd into d cube n by GD power 4. Okay, if you solve this by cancelling the 8 and 8, we get pi d cube, pi into tau into d square n by k into d into g. By cancelling this d power 4 and d cube, we get this. Okay, if we substitute the W and delta values in this U relation, U is equal to half WD, we get half into pi d cube into tau by 8 kd into pi into tau into d square n by k into d into g. Okay, now we are writing this relation in terms of volume. Okay, the volume is pi d n. That pi d will be the area of the spring wire and n will be the number of coils. Okay, that into pi by 4 d square. That pi by 4 d square is the overall so this pi by 4 d square is the area of the spring wire, and the length of the spring wire is pi d into n, which will be the perimeter. See, if you take, this is the one coil, if you cut it here, then it will be like this, a line. If you cut and open the coil, it will be like this, and this area, it will look like this. There will be some thickness, right? That will be, this length will be pi d, pi into d. Okay, and if you take the number of coils, n, this is only one coil, right? If you take number of coils, then it will be into n. Okay, pi d into n, you get the number of coils, and this area will be pi by 4 d square, pi by 4 d square. This area of the rod will be the pi by 4 d square. If you take the pi by 4 d square into pi d into n, this pi by 4 d square is the vertical, and the horizontal will be the pi d into h. This is the pi by 4 d square is the cross section, that cross section of the coil, cross section of the coil. Okay, or spring wire. This is the cross section of the spring wire. By this we get this volume of the spring wire, and the remaining part will be tau square by 4k square into g. Okay, then this is the final relation we got, tau square by 4k square into g into v. This is the final relation. Okay, and note that when a load falls on the spring, this is when a load is falling from a distance h, from height h. Okay, then if you want to find out the energy stored, or if you want to find out the energy, we use this relation, P into H plus delta is equal to half into W into delta, where W is the equivalent static load. Okay, that is the gradually applied load which shall produce the same effect by the falling load P. Okay, this W, we have to take the gradually applied load which will be equivalent to the falling load P. Okay, the equivalent load we should take the W, and delta will be the deflection of the spring. Okay, next topic is helical spring subjected to fatigue loading. Okay, the helical spring subjected to fatigue loading are designed by using the Soderberg line method. You know that we have already learned this Soderberg technique. The spring materials are usually tested for torsional endurance strength under a repeated stress that varies from 0 to a maximum. These springs are operated by using this torsional endurance strength, where the repeated stresses varies from 0 to maximum. Since the springs are ordinarily loaded in one direction only, because there is no reversal loadings, therefore a modified Soderberg diagram is used for the springs. Here we see there is a modified Soderberg diagram. This is the modified Soderberg diagram. Here the point, let's see the construction of this diagram. This point, here the x-axis is mean stress and y-axis is variable stress. This point A is the endurance limit for reversal loading. This A point is the endurance limit for reversal loading, where the variable shear stress and mean stress are tau e by 2. Okay, this is the value of that A point, tau e by 2 and tau e by 2. Okay, endurance limit by 2. And there is a point B, which is SSY, shear yield strength, or tau y. This B point is shear yield strength. We know that SSY, or it is represented by tau y. Okay, then you need to draw another safe stress line by considering the factor of safety, FOS. Okay, this is the ultimate line or Soderberg line, that is failure stress line, where if any point falls above this line, the design is not safe. Okay, this is the failure stress line. So we are considering the factor of safety. By considering the factor of safety, here we are having another line, which is the safe stress line. Okay, by considering factor of safety to yield point, this yield point. Okay, then we got this point D. Okay, if you consider factor of safety for this yield point, we got this point D. By using this, if you draw a parallel line to Soderberg line, we will get the CD. Okay, this line CD. Okay, after that, for the design point of view, you have to take some point which will be at tau m. This is the mean stress, and tau v, which is the variable stress. Okay, by using this point P, we are designing this formula relations. Now see, from similar triangles PQD and AOB, here you see PQD, this is one triangle, and AOB, this is another triangle. If you see, PQ by QD is equal to AO or OA by OB, AO by OB or OA by OB, that we have taken here. Now QD and OB, QD, this value QD is equal to O dash D minus O dash Q, O dash D minus O dash Q, where O dash D is tau y by FOS and O dash Q is tau m. Okay, tau y by FOS and tau m, and PQ is equal to tau v. Okay, variable stress tau v, and OA is equal to tau e by 2, OA is equal to tau e by 2, and O dash B and O1B minus O1O, O1B will be tau y, O1O will be tau e by 2. See, tau y and tau e by 2. Okay, by simplifying this relation we get tau e by 2 tau y minus tau e. Okay, if you simplify this relation, we get tau e into tau y by fs is equal to 2 into tau v tau y minus tau v tau e plus tau m tau e. Okay, if you divided both sides with tau v into tau y, we get a factor of safety relation. By using this relation, you can find out the factor of safety. Okay, but if you want to find out the factor of safety, you need to know these values, tau m, tau v, okay, tau y and tau e. Okay, and tau y and tau e are the this is shear yield strength value, and this is ultimate strength value. Okay, tau m and tau v you need to find out using the relations. Okay, so for finding out the mean shear stress tau m, Ks into 8Wm into d by pi dq, where Ks is equal to 1 plus 1 by 2c, and Wm is equal to W max plus W minimum by 2. Okay, by using these relations, you need to find out the tau m. Next, for variable shear stress, tau v is equal to K into 8Wv into d by pi dq. Okay, this is a mean load. For mean load, maximum load plus minimum load by 2. Here you need to calculate variable load WV. For variable load, W max minus W minimum by 2 you need to calculate, and this K is the Wahl's factor, 4C minus 1 by 4C minus 4 plus 0.615 by C. By using these relations you need to find out the FOS, okay, factor of safety for the spring. Next, see another small concept, springs in series. If springs are connected in series, if you want to calculate the overall stiffness, okay, or combined stiffness of the springs, you need to follow this. Here if load is acted like this along the axis, if the springs are connected one over the other, this is called springs, this arrangement is called springs in series, okay, for they are connected like this. Here the delta will be delta 1 plus delta 2, okay, the change in length or deflection, the deflection delta will be delta 1 plus delta 2, overall delta will be, and we know that stiffness K is equal to W by delta, okay, then delta is equal to W by K, delta 1 is equal to W by K1, delta 2 is equal to W by K2, okay. This W will be cancelled, okay, this load W will be acting, the same W is acting on both the springs, okay, so this load W will be cancelled, then we get 1 by K is equal to 1 by K1 plus 1 by K2. This relation you have to use to find the combined stiffness of the springs, okay. Now see springs in parallel. If you take springs in parallel, this load W was if you take that W, this W will be shared between the two springs K1 and K2. This K1 will take W1 load and this K2 will take W2 load, okay. Then W is equal to delta into K. From the, we know that stiffness is equal to W by delta. From that relation you can know this, W is equal to delta into K, okay. Since W1 is equal to delta into K1, W2 is equal to delta into K2. If you cancel this delta terms, K is equal to, if you take out delta common, you can cancel delta and delta, we get K is equal to K1 plus K2. Then you can find the K combined stiffness of the springs, and delta is the deflection. See, surge in springs or finding natural frequency of helical spring. This topic we have already discussed. It is similar to the resonance. We have already discussed that when the soldiers march on a bridge, okay, the resonance will occur, and if that frequency of the marching and that frequency of the natural frequency of the bridge matches, the bridge will collapse, okay. In similar way, if the natural frequency of the spring equals to the vibrations in that spring, then the spring will fail, okay. For finding out those natural frequency, we need to use this relation, Fn is equal to d by 2 pi d square into n into root over 6g g by rho, okay. This natural frequency we are finding out for the spring, okay. If this spring is used in a mission, okay, if the mission causes the frequency which was equal to this natural frequency of the helical spring, then the spring will fail, okay. So the vibrations or the frequencies causing by the equipment should be less than this, okay, less than this natural frequency, then the spring won't fail, okay. For that purpose we have to calculate this natural frequency for helical spring for a safe design. If you want to eliminate this surge in springs, we have to follow these methods by using friction dampers on the center coil so that the wave propagation dies out. You can use this element called friction dampers on the center of the coils, inside the coils, which will cut off the propagation of the wave, okay. The waves will propagate throughout the spring, right, when any impacts are acted on the spring, those will be cut off by using these friction dampers or by using springs of high natural frequency. If you are if the equipment is acting at some value, the equipment frequencies are at some value, you need to take some higher value, higher natural frequency helical spring to compensate those frequencies of that equipment. Okay, if you take higher natural frequency springs, then that can be eliminated. Okay, by using springs having pitch of the coils near the ends different than at the center to have different natural frequencies. You can also use this pitch variation compared to the center of the coils. The end of the coils will take the different pitch, then the natural frequencies will differ and the spring won't fail. Okay, you can also use this method. These are the methods to eliminate the surge in springs. Okay, thank you. You can refer RS Gurmi for this lecture. Thank you.